Hey guys, Sándor from Migrating AI here. In this video I will explain how you can migrate your Python notebook into its own project and run multi-GPU training on it. Now I created a repository on GitHub, it's public, you can clone it, fork it and use it for your own experiments. Now clarification, this video is about training your own custom deep learning models from scratch for research purposes. So in the previous videos we had a notebook, something like this, where we loaded our dataset, created our modules for our neural network, the encoder, the decoder, the vector quantizer, ran our training with various parameters, and we ran some evaluations manually on it by showing GIFs and other kinds of stuff. Now the problem with this after a while is, as you can see, it's getting pretty long and it's a single file. So, and the other problem, besides that maintenance is getting harder, is that the training runs on a single GPU. And if you have access to multiple GPUs or you want to run it on the cloud on multiple GPUs, then it's going to be a problem. So the model gets bigger and bigger, and also you have to wait longer and longer, even for your own tiny model. So sooner or later, it's inevitable that we will have to move it to a project. This is what I created, and I will quickly go through it. So starting from model.py, actually, as you can see, the folder structure is that there is a generic lab folder and a shared data folder for various data sets. I will extend these as they come. And here's the models folder. Currently, the soft TW GAN is here, which is what I called my own little model. And I intend these to be completely self-contained besides the data folder. So this means that you can copy these out and run them by themselves, so they don't depend on anything else besides this currently the Faces 120 dataset. So this is not much more than what we had previously in the notebook. One exception is that it's wrapped in a class, but it's also the static method. And since we are running distributed training, instead of providing the shuffle parameter here in the train data loader, so this parameter, we used to have shuffle true. Now we have to use a distributed sampler. And the num replicas is the word size. The word size is, in this case, on one machine, and two GPUs will be 2. So we have 2 GPUs, and the rank is the index of the GPU, so 0 or 1. And we provide the shuffle parameter here. So this distributed sampler is passed to the training data loader. And this ensures, of course, that one GPU, when it picks a batch, the other GPU won't pick that same batch. By the way, you can just disable this, and then you need to provide the shuffle true parameter, even with FSDP on this multi-GPU setup. Where the downside is that both the GPUs will run the same data set, so you will have no speed up almost at all, because it's just running duplicate training on the whole data set. So the distributed sampler is crucial for getting that speed up. And yeah, one more tiny change is that I increased the batch size for testing. It's faster, and because we are just running this in inference mode, it doesn't need to reserve the memory for the gradients and other training parameters. So since we have more free memory, we can increase the batch size. You can tweak this around. Probably this can go a lot higher as well. So this is our dataset loader. Pretty much the same as before. I just passed the sampler additionally here. Not even sure if I use it anywhere, but so going to the model, this is almost exactly the same as in the notebook. This is not the soft VQ VEA model from the last episode. This is a bit more complex model, but in this model Python source file, you would put all the model definitions from your notebook. So yeah, there's a patch embedding, an MLP, a tension, a transformer block, and the encoder. So in the last episode and in the previous episode, we used a convolutional encoder. Now here, this is a little bit different because this patch embed breaks up the input image into 4x4 patches. So it doesn't really go with downsample, 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 downsample incrementally. It just splits up it into patches, and then these patches are fed into a number of transformer blocks. And the decoder I kept kind of the same with an additional convolutional layer here, which keeps the size just to be able to store more information. And this discriminator, I think we will talk about this in a later video. The soft vector quantizer is almost completely the same as in the last episode, except that since we are doing FSDP, fully sharded data parallel training, that means FSDP, it doesn't only split the data, so our data loader with the distributed sampler to one GPU and the other GPU, it also splits up the model parameters, the weights, the tensors. So this means this codebook here will be, or might be, at any point in time, split across GPUs. So half of the weight is here, half of the weight is there. And since we are accessing this codebook right here, we wouldn't be able to without this line. Because it's not a full matrix at any given point in time, it's not guaranteed to be. But if we wrap it with FSDP, that's sum on full params for the notebook, and write back is false because we are not writing it here in the forward pass. It will be written in the backward pass, but in the forward pass we don't have to care about that. So this will just ensure that we can access the full codebook's complete weights and use it for calculating the distances and then the probabilities and etc. for the soft VQ. Tiny utility class. This is so just in case later the model will definitely have many parameters, and it's a utility to load from a YAML config, and here is just passed to the main model. This is the main model. So talking about YAML config, very simple one. As you can see, the model params. This is the same that I just showed you. There is a fixed seed, so we kind of run our training deterministically. We can define the batch size here, the maximum number of epochs, and two learning rates. One for the primary model, which is in case it's called G for generator, because it generates images, and one for the discriminator because it's again it discriminates the generated image called a fake image from the real image, and as you train it, it along the way it also learns how to discriminate and identify which image is real and which is not real, in brief. And so the next would be the train Python source file. This is the file that you run the training with. This make file is basically just a command runner, so you can type make train. It's just like npm scripts. It's a bit older, it's simpler, and it's cool. So make train command will execute this command. nccl shm disable equals 1 is only needed if you're running Ubuntu in WSL. I believe in normal Ubuntu it's not needed. And torch run is a utility that you can you have to run your distributed training scripts. So you can just go and say Python src.train. This won't work because this train Python file will be ran twice. So torch run executes this file twice and does a few other stuff as well. And having said that, from now on we have to treat the whole source code as if it was run, because it is, on different processes. So the same code executes parallelly in different processes. That's why at some places we have to sync up those processes, and we cannot anymore calculate just losses in a single array locally, because that would mean that in a single process you calculate the losses, and in another single process the same code calculates the same losses, but they are local losses. So a loss on one GPU and loss on the other GPU. So to calculate for example, the final loss at each epoch, you need to call a function, a torch distributed built-in function, to sum up these two losses, to reduce them into a single variable, and then you can print it or log it. So here we just import our data set. There's a trainer separate file, some arguments. The config is by default the config YAML I showed you, but you can change it to some other config if you'd like with this argument. The load argument accepts a timestamp in this format because I save the checkpoints locally for now, and the ID for them is this kind of timestamp. So if we go to this checkpoints folder, as you can see, there are many timestamps. The latest is this one. So there's the discriminator model, there's the generator model, the optimizer states, and also one ONNX model for deployment. I haven't yet tested this. If you'd like, you can load it with ONNX in your Pytorch script. So we load the YAML, and here, as you can see, each instance of this training Python file receives an environment variable, local rank. So for GPU 0, so the first GPU, this will be 0, the second GPU will be 1, and for the third 2, and so on, as many GPUs you have. If you have like 8 GPUs because you're running a DGX, then you can set this to 8 and it will scale up. So it, as you can see, it selects the device based on the rank. Some few more configurations. This initializes this process group of these processes that I mentioned. We seed everything, and from now on you should assume that everything otherwise stated runs in its own process. So all the code, for example this, runs on each of the process, communicating with its own GPU device. Except there are, of course, some built-in Pytorch functions that under the hood synchronize these processes. So as the code runs in parallel and you call a specific Pytorch function, all the processes, well, that one process that initiates it will wait for all the other processes to finish whatever they are doing and arrive at the same line. I'll detail this in a few minutes. So we set the precision, load the dataset, initialize our model trainer. This loads the model parameters from that specific area of the YAML file. So it loads only this. And so on. And then we train the model using the fit for a number of epochs defined also in the YAML. Now the model trainer is a bit longer. So actually here's the initialization code. And it receives the rank parameter and stores it, also the device and many more. Now this line will be useful at a few places. If we were just to do this and print, in the console you would see as many lines printed, the same thing, as many processes you run. Because as I said, everything runs on each process. So when you're printing, you have to check if your rank is 0. So if this script is running on process 0 and only print once. You can print on basically on any other rank, but rank 0 is the ideal. And we create our model normally, just as we did before. Now here we can define a mixed precision policy. And the output type is float 32, so each, I think each layer's output and the final output, we keep it in float 32. I tried to change this as well to half precision, brain float 16, but didn't yield as good results, but you can go and experiment with it. Now the parameters, so the weights are stored in B float 16. That's kind of good enough. It can, I mean, many state-of-the-art models are trained with similar configuration, so the weights are 16 bit floats. The reduce type is, I believe, for interprocess communication. And the output type, as I said, it's for the output. Now, we are using FSDP 2 of Pytorch. I tried using Accelerate, see if it's simpler, but it's made for pre-trained models, and if you use specific well-supported public models from frameworks, specific transformer blocks, etc., not your own, then it can shard it pretty well across GPUs. But I'm using a completely custom model with a custom transformer block, and accelerate, it cannot really shard it. As opposed to the native Pytorch FSDP, whatever model you have, it shards it across the GPUs. So there's this auto FSDP wrap utility function. It's in utils.fsdp. I asked ChatGPT to write this because I didn't want to deal with it. It's basically, it does a depth first search because how you need to wrap this fully shard command comes from distributed.fsdp, and let me just remove these multiple imports. So you need to call fully shard on your model, but before you call it on your model, you have to call it on each layer. Now, generally, except for toy models, we would have very nested and complicated models. So when you go from the root model, you have to perform a depth first search. So first, this fully shard is applied to the leaf component and applied to each of its layers. And then as it goes up, it applies backwards back to the root component. From experiments, this worked pretty well. I haven't completely verified if it shards 100% properly. Probably not, because it's ChatGPT written, but it works pretty well. Also, there might be other auto wrap policies in torch.distributed.fsdp.wrap. So there's always wrap, lambda, auto wrap, transformer. This is for I think that kind of transformers that are supported out of the box, and so on. So maybe, I'm not yet sure, but I will look into it later, that this auto FSD wrap can be replaced with that built-in function. So we just recursively wrap both of our models. This will convert the tensors into D tensors, I guess distributed tensors, and split across the devices. Then I set up the optimizers and some other parameters. Load the checkpoint if there is a load argument given. And this is new. I think TensorFlow had it long ago too, where I think in TensorFlow you always had to compile your model. But in Pytorch, this is relatively new, a few years old. And applying this after the FSDP wrap, I think it's the only way. So this compiles the kernels into much more optimized, faster CUDA kernels, lowers memory footprint. So basically just compile your model because it will be smaller, faster, and better. So as I said, we load our model. And in this case, there are two models. And I also pass the optimizers for each model. And this load checkpoint function in the top of the file called this.barrier first. So this is the function that I mentioned. This will wait for all processes and make them stop and wait there. So it syncs up the processes. And we just perform a torch.load on the model So the checkpoint is saved in this format. It's 5 files. It's either model D or model G and the optimizer state. Now set model state dict and set optimizer state dict is imported from torch distributed checkpoint, that state dict, because this needs to take all the tensors loaded into model state dict and spread them across the sharding policy, across all the GPUs. So you can just say model set state dict, it will not work. And the same goes for the optimizer state. Similarly, when you save a checkpoint, I call this dot barrier, and you need to call get model state dict or get optimizer state dict, because with these parameters, because this will collect all the shards from all the GPUs and into a single model on the CPU. So now you have a full model state dict or a full optimizer state dict, and you can save them using torch.save. Now you can globally call this dist.getRun function. So dist here is just torch.distributed, and we would want to save it only once, so not in all processors multiple times. So if we are on rank 1, then we save the model and the optimizer state dict to here. Alrighty. There's another handy utility function. When I save the model into these PT files, I also saved it to an ONNX file, but I haven't actually tested this. And as I see, yeah, this is buggy. I will fix it because this used to write the full model and now it's writing to the ONNX file. So let's write it here, and this will be full.pt. So it saves a full model file, not only the weights, and it also saves this ONNX file. Now, as far as I know, for inference, when you want to load an ONNX, that model has to fit into a single GPU. You can do DDP inference on it, or training further maybe, but if your model is so big that even for inference you have to shard it, then so far as I understand, you cannot use ONNX. In that case, you have to load your model, the full model, in Pytorch using torch.load, and you can run inference with deep speed because that automatically shards, or you can just run inference with FSDP as we do here for the training. Now I use MLflow for these experiments. I don't save any artifacts or use any data from it because I use data from Hugging Face. But I upload the model parameters and run experiments. If I can just pull it up. Yeah, so just basically uploading the charts here. It's really nice for this kind of purpose, and it stores the runs as well. As you can see, it starts a new run for everything, which might be an overkill, but it is what it is for now. So this ML flow start, it runs here. And before that, I run an evaluation, an initial evaluation of the model. And I do this because if any mistake is made in the model itself, for example, tensor operations are incompatible because some dimensions are off, or etc., then this will not start a new ML flow run, which would be empty anyway because it would crash the next line. And also it returns the initial total loss. So this is a good test whether to see if our model works or not. And as I mentioned, so we use a distributed sampler for our training data set, and this sampler, it requires that for each epoch, that's why I exported it, you need to set the epoch. So I believe then it reshuffles the data set. And yeah, just set the model to training mode, increment the total epochs. And this local matrix, this is the trainer matrix file here. So local matrix, it's local because it's per process, or you can think of it as per GPU. There's a learning rate, which itself is not local, but the local matrix will be converted to global matrix, so it's a handy place to store these here as well. There's no hurt in it. And of course, there's always a train loss and evaluation loss, which are local trackings, because there are many kinds of losses. So the generator loss, the discriminator loss, reconstruction loss, which is actually the sum of the L1 loss and the structural similarity index. And because we are working with a vector quantized variational autoencoder, or at least with a code book, in this case, perplexity is kept track of. And we will come back to this file a bit later. So yeah, just for each epoch, create a new local matrix. In some cases, you don't need to train the discriminator in every epoch. Well, I did here, but here you can see various policies of how to train it, because the discriminator has to kind of train at the same speed in order to be able to compete with the generator. If the discriminator, which it learns too fast, and it tends to learn too fast, if it's trained at the same learning rate and in every epoch, then after a while it will just refuse all the fake images that the generator creates, because it will be so perfect in distinguishing the generated images from the real images that it will just reject all. So in this way, the generator won't be able to train further. Kind of feels like when someone is learning and you give them rewards and rewards, they stay motivated to learn. But if you don't reward any progress that they make, they will just fail to learn. Anyway, it's an analogy. So in this case, we iterate through the training data set, the training loader with the distributed sampler, and TQDM is just, it creates a nice progress bar in console. Actually, yes, because I moved it. inside here. So I will run this file, and it became lab modal soft tvgan, no typo, no typo. It takes a bit to initialize the processes. As you can see, 2 prints, and I print this here. So when you just print like this, it will be printed on all processes. But model parameters is printed only once, because we check for rank 0. And this is TQDM. It just creates a nice progress bar. And this table is also ChatGPT generated in train metrics. Again, there are more important stuff than spending time on printing a table to console. I don't think this is any way different than using a library before. However, now we generate it with AI instead of doing an npm search or some Python package search, and it can generate it in a more personal, specific way. So yeah, training is running. I will cancel it now. And let's continue. So here, this is basically, we move to the selected device or batch of images. All of this you can replace with your own training code. The training here is made up of 2 parts, because we have to train the discriminator and we have to train the main model, the generator. And this local matrix, as I showed here, has a list of tensors. This is logged. For D here, the D loss, and the reconstruction, the similarity, the total loss, etc. are logged here. But remember, this is per process. So this code executes because there is a self.device. Not because, but as you can see, there's a self.device here, meaning this will execute on one device. So you collect these losses into an array for each process. And here, there's some other code here for running the evaluation and saving the checkpoint and stopping the learning day scheduler. But here, the global matrix this code, as you can see, it goes through self.trained to means, and to means stacks up all these values because we have a normal list of tensors, and those tensors are just a scalar, basically one value, one float. So this stacks it up, and to make a tensor, not a normal list from them, calculates the mean, and it has to reduce the mean, is what I mentioned. So for each stacks of these tensors, we clone and detach them from the computation from AutoGrad, basically. And this all reduce is a function that just does that. So when you have n tensors on n processes, it can reduce them into one. And how? You can define the operation, and in this case, it adds them together, so it creates a summary. And to arrive at mean values, average values, we divide it by the world size. And the world size here is how many GPUs you have. So this two-global matrix function, it implicitly calls this dot barrier. All reduce does implicitly, otherwise you wouldn't be able to calculate because GPU 1, for example, was faster, it finished calculation, but GPU 2 hasn't finished that epoch. So it has to wait for all the arrays to be, all the lists of losses to be filled up. So it implicitly creates a barrier and reduces all the tensors into one. So in this case, G matrix will be the global matrix reduced from all GPUs. And if we are on rank 0 to avoid printing this multiple times, it prints that table you saw before and log the MLflow matrix from G matrix to create those nice charts. Now, not much is left. Init codebook is not exactly used here. I found it better not to use it, but feel free to experiment with it. Now, evaluation model, I actually call this dot barrier in the beginning and in the end, just to be sure. It might be an overkill, but so this basically just runs through the test data set, logs the losses, and it reduces the same way into a single average loss, which returns that. This is just one loss, just an indicative something, but it also logs all the losses. So in global matrix, this will get sent to MLflow and uploaded into the chart. We have an end file. This is your Hugging Face token to pull any data set you want. I believe this is not yet needed. You can set these up, but it's not uploading anything yet. Now I will remove this from the video. And the rest I believe are needed, but when you register to MLflow, then it will print these variables out, so there's no trouble there. Now one more thing, here is this inference notebook, and I made it so we can easily display GIFs, images, and whatever data here using matplotlib, even charts. So it does the same. It loads the data set. You can load any data, it's not required, but I just tested it with that, and it imports the model. Same way it loads the same configuration as the model was saved. As you can see here, you can put the timestamp and you will have model G. It loads, and this loads into a single GPU. So there is no FSDP here. This loads the model into a single GPU. And we have our utility functions to show GIFs, save GIFs or images. And here's some code to just run inference. And here you can see the reconstruction quality is not so great in this case. It wasn't trained for so much. It has a fit test, has a 79 score. And yeah, I guess that was the best I could achieve, a 15.69. with wide clipping W-gun and 2 transformers. So the feed, the fresh at inception distance, yeah, it's a widely used metric to measure image reconstruction quality. Others are, so we have the FID, the PSNR, the L1 loss, and the L2 loss. Basically, you can use these four to measure how well how well you reconstructed the image. So this has an implementation here. Under the hood, it uses a neural network, I believe, VGG or its own, I'm not sure. The same utility functions are here, and to seed everything, seeds Python random, NumPy, Torch, and set some QNN variables. So I made a repository public, and I will leave a link in the description. It's at github.com/ubitonai with caps /experiments. There's a small description here, and feel free to clone it, fork it, use it, and open up issues if you find any. I'm sure there are a few. I intend to continually evolve this project. I will probably not touch the soft TWGAN model, just a little bit, and then always make an entirely new model and improve the general architecture and the framework there. So with that said, thanks for watching. Please subscribe for more, and yeah, see you next time.